Okay, induction. So, can write that down. Okay, continue. You have that? So, yeah, a bit to do, all right. Okay, so we have seen that a moving charge in a magnetic field will experience a force. What happens if we move the magnetic field? So here's a good example of this little experiment here. You have a copper wire, and you have a voltmeter here, and you have a magnetic field. But then what you do is you move the magnetic field, and you notice that you get a voltage. And you stop moving, and the voltage goes back to 0. So this is quite interesting. This experiment suggests that if you move a magnetic field near a conductor, you can make a voltage. You can make a flow of electrons. And this is actually really, really useful, because this is how you make electricity. The idea. Yeah.
Regenerative braking.
Yes. The hybrids. Yeah. Even your little light on your bicycle as well, maybe. Yeah. The dynamo. Yeah. Anyways, this is a simple picture of what's called electromagnetic induction. It's a very, very, very simple experiment. In fact, I would like you to draw this. It's a very simple experiment for electromagnetic induction. Okie dokie. You got that drawn? Yeah? Continue? Guys, continue? Okay. Continue? Diego, have you got this? Can I continue?
I'm just trying.
Oh, come on, what's taking so long? Okay. Right. Note, while the magnetic field is moving, a voltage will register on the voltmeter. Now, we need to give a definition of electromagnetic induction. So, based off of this picture, does anyone think they can fill in the sentence here? Electromagnetic induction is... Gina looks like she knows. Go on. It looks like you know. No? Ah, you sure? Oh, okay. Alright. Lynn?
No.
Don't even want to try? Go on, you can practice your English.
I don't even know what it is.
It's this process
Yeah.
in a sentence. Electromagnetic induction is... When? Go on. Is when, yeah.
Current is produced.
Yeah.
Conductor.
Yeah.
When a magnetic field
Yeah.
moves through it.
Yeah, that'll do. How did I write it actually? Electromagnetic induction is production of an electromotive force, i.e. a voltage, across a conductor, like the copper wire, exposed to a time varying magnetic field. So, simple English, induction is producing a voltage in a conductor when you change a magnetic field around it. Is that okay for people? Are you having a heart attack?
No, it's like, you know that chill that gets sent down your spine when you chalk on a chalkboard with a nail?
Where did that come from?
The pencil.
Oh, right.
It's painful, right?
Try not to have a heart attack, though.
On first aid trace.
Rates your soul.
Alright, have we got that? No, not yet.
Where's the time?
Yeah. Very magnetic field.
Position, not time.
No, well, what I mean is,
Position and time.
at different times you have different magnetic fields. So it could be that it moves, or gets stronger, or gets weaker. The one thing that all those situations have in common is the different magnetic field at a different time. Yeah. Is everything okay in this, Gina? Any of the words confusing? So you just check in.
Okay to say current as well, so we have to hide that voltage.
Yeah, I can't see any problem with that.
No current.
Okay, continue. So, yeah. We have two laws regarding electromagnetic induction. The two laws are, firstly, we have what's called Lenz's law, and he said that if an induced current flows, its direction is always such that it will oppose the change which produced it. Now, before you write that down, I'll give you an example with a picture.
It's his left hand motor. I remember.
You remember this one? So look here, look. The magnetic field is moving to the right. Okay, it's going to the right. See? So which way will the current move? According to Lenz's law, it flows to oppose. So as the magnetic field enters from the right, the current will run to the left. It's almost like the current is running to meet the north field that's entering here. Okay. Now in this picture here, there's the north. The north is being pulled out. So as the north field exits here, the current runs the other way, away from it. The current does the opposite of what the magnetic field does.
Why does that happen? Why does that happen?
Ask Lenz. I don't know.
Be hard.
So,
Think about it.
like here,
Electrons are propelled.
yeah, I think the picture tries to explain it. So look, here's the wire. Here's the magnet. There's north, there's south. There's the magnetic field. Okay, so if I was to push this in here, I'm pushing the north into the conductor. This will make the current run backwards this way. The current will run out here. Remember, opposite. So if I enter the north on the left, the current will exit on the left. Like in the picture here. I put the north in on the left, the current will exit on the left. I exit the north on the left, the current will enter on the left.
So does it have to, is it pole dependent as well?
If this was flipped around, so S was here and north was here,
It would be the same as the other image.
it'd be the same as this image,
Yeah.
except you'd be pushing it right. So the current would be going out this way.
Yeah, it's not the same.
Well, it's going out this way here though.
Yeah, but if the south pole went in first.
Whew, if the south pole went in first. Oh wait, no, both these are, sorry, north, south, yeah. If I flip this upside down and have north and south here, then this should be going the opposite way, going in.
Yeah, it would be the same as the other.
Wouldn't it be still the same?
Would it?
Well, yeah, it's like if you mirror the second
Yeah.
image.
Good grief, it's getting complicated.
Yeah, it's like if you mirror the second image.
If you mirror the second
It's like
image,
that. So if you flip the magnet, it becomes.
my brain.
Goes north, north, so south, south.
If you put south, it should
So
just
the current
become
will
south
go-
again, the other one.
So it just vertically flip them
No, I think
across the
whatever.
y-axis.
Oh.
It's easier to say if you put north into it, then that part becomes north. If you put south into it, that part becomes south.
But
But you pull it away, then the north becomes south. And you pull it away, then the south becomes north.
if you do what with the what now? If you put this in,
Then the coil would be the pole at the coil that at the end of the coil which you put the magnet in
yeah.
would become the same pole as the one that you're putting it into. But when you put it
But
out,
then
then
why,
it
as
will
you
become
move it, it
different.
doesn't flip sides then?
I don't know, but that's how I think that's how I learned it.
Because then the south would be, end of the magnet would be,
I think it's
Mr. Google.
the thing is there wasn't any north and south in the coil in the first place.
Yeah,
It's just
Because
it's
when you
just
put it
created
in, then yeah.
okay, what we need is 4 pictures
Yeah.
of the 4 possibilities. That's what we need.
And what happens if you put the whole magnet inside?
And then what if you stick it in your mouth and then spit it out?
Oh, there you
Come
go.
on,
Big
man.
fun.
Come on, I have enough to be. Okay. Let's see what Mr. Google says. Lenz's law. Let's get.
Oh, I like it.
Yeah. This one?
Is it?
Oh, I don't like this one. I want. Yeah.
There, that one.
This one?
South,
See,
yeah.
south comes south, and then
It's the same as the other
comes
ones,
north.
opposed.
Oh, I don't like this one either. You like it.
That one. There.
that's Faraday.
Oh,
That's okay.
Wait, what was it?
Faraday.
This is
Uh,
the last.
Google lenses law and give us Faraday's law.
Just Google it. You
Well, you might also be interested
That one
in
there.
this, you know.
Yeah.
No, that's what.
I think it should be. interesting.
Lenz's. Oh, well, hang on. I'll put an S here, will I? Lenz's law, 4 examples. Okay, let's see. Oh, do I want to look at this one?
Maybe check down. Maybe you can-
Oh,
That's the
okay,
Wikipedia image.
okay.
Well, it's basically the same, right? It's just a big coin.
Why is it?
All right,
That's still
fine.
cool.
Oh, yeah, yeah.
I can't.
Lenses law.
Right.
Can you put that in bigger?
This is what I. Hang on. Okay. No, this is as good as it can get, I'm afraid.
It's far become.
So no.
Really, is this any better?
Where is north in the coin?
Oh,
Or south or whatever?
What's this one? No change, no current. Why? Oh, because you're not moving it, so it's stationary.
No.
No current. Okay. You move this down, and you get a current running this way,
No.
around this direction. Okay. You move this up, and what the heck is happening here? The current goes the other way. Right, so this is what you guys are looking for. It's all the possibilities.
Yeah.
So you were asking me, which one were you asking me, Diego? What if you have the south here
Yeah.
and the north here?
Yeah.
So that's going to be one of these guys, where the north is the other way. And are you putting it in or out?
Same, it should be same.
Yeah.
Put it in. So that's this one, D.
So the
Then it's
the
flowing
current goes.
And the current
opposite
goes
of north,
clockwise, if I'm looking from the top.
clockwise. Yeah.
So that would make it going clockwise here. So opposite.
Yeah.
Oh, good grief. Yeah, okay. Yeah, okay, so there you go. There are the... We really just care about these four possibilities, isn't it?
Mm-hmm.
Because if we don't move it, we get no current. And what's wrong with this one?
The current is going the opposite way. As
Yeah,
you
but
said.
what are they doing here?
violation of Lenz's law. Induced flux in the same direction as B.
Don't know. Don't want to know.
Because they're showing the field as going
Oh,
around.
look, you've got a rule here. Right-hand rule.
That's why it's this
That's
one.
the.
Because if it's still
the-
going like this, then
Thumb.
it is true that it is becoming
So
south.
if the magnet is,
It does become south.
so the current would flow this way, and then your thumb points to the north.
No,
Wait, what?
no the thumb is
Yeah.
the
The thumb is
No,
north.
The
no,
cur-
look,
the current.
because if you put it on B and you put north on the thumb,
It's right, did it?
look at, well,
Oh no.
no,
it's
it's not. You should put it
On south.
south,
yeah.
and then it will give it to you, but not because you have number C, which is opposite, so it doesn't work. You can't do it with your hand.
We need some kind of hand rule here, don't we?
I guess
But it doesn't work with
it
the hand.
becomes north and north, south and
The
south.
current moves to the direction of your thumb, and the magnetic field curves to the direction
So
of your
if
fingers.
say the this part becomes south and it goes like this, then it should just be like this.
Look at B. You do that on B, and it
Yeah.
works. But then you do it on C, and it
Yeah,
doesn't.
that's because that part becomes south now. It doesn't, you know, the part where it's exiting to, now it's becoming south pole, not the north pole.
Whoa.
We want some nice little handy Lenz's law hand rule. Isn't that what we're looking for? Maybe we have one.
Right? Fleming's right hand.
No, we did Fleming's right hand rule already.
Fleming's
Why
left
is
hand rule.
this covered?
It's Fleming's left hand rule.
Oh, here, right hand induction.
Yeah, the one we learned was
Whoa.
left hand rule.
Okay.
How is it like that? Looks like this.
Dude, what is that?
It looks like this, but
Dude, how do you even?
no, I think it's like that.
It's this, isn't it?
It's the same as
No, it's
the
like
left
this.
hand, just
It's like this,
Like that. So
Yeah.
but because they took it from up, it looks like
Yeah,
that.
so
More.
current, motion, field, field with north here, current here, motion here. Shall we try
It's
this?
the same
Fleming's rule.
No.
No,
it's not.
this is a magnet now.
That's Fleming's rule. The one we learned is
North
left hand.
to
So it's pointing south. You have to
The one we
remember
learned was
south.
Fleming's left hand.
Because it
This
goes
one is
from north
induction.
to south.
Right hand. It's different.
I thought that is Fleming's rule.
No, we start. Okay, look. See, now remember I told you we'll mix the hand rules up, and you're like, no, I'll remember. So we started off with Fleming's right-hand grip rule. Then we had Fleming's left-hand rule for the force, calculating the force.
Yeah.
Now we might have a right-hand rule here for this Lenz's law. Oh my goodness. Which current, motion.
But you point to this.
Yes, because they are perpendicular. So this is the motion the current flows, and then if it's changed to the motion of the magnetic field, then the current would go in the opposite direction.
Wait, what?
It's just
North
funny.
to
I
south.
just don't understand the motion now.
Yeah, because this finger is the motion, isn't it?
I don't understand the motion.
Go.
But it kind of
The
looks like
current
these
and-
two are in the same direction in the picture,
Hold
like
on.
this.
How do you do motion?
Yeah.
It's going in the same.
I guess it could be something. It's not. Yeah. The motion could be just something else. But this thing then, we moved the
Why
time
are we so confused?
because it's confusing.
They're not. This isn't for the exam, anyways, so we don't need to worry about it. I just wanted to give you a picture of the idea, but I will worry about this tonight as I'm sleeping.
Oh, there you have it.
Oh, where?
That one. Magnet motion.
No, that's not quite it.
Yeah.
Still the same.
That looks so wrong.
Fleming's right hand. Cool.
Oh, that
Ah.
one maybe. YouTube part 1. Left.
This
hand
one?
rule.
When you put in south and south, north and north.
This one?
No, the YouTube
This one?
The YouTube.
The YouTube one?
Because
I don't have sound on my laptop.
But I think he'll just draw it out. Because look, it's north, south, north, south, south.
Oh,
north, south.
okay. Right, he's got the 4 possibilities here. Good man. Right. So, which 2 do we have? We have
The north,
this one,
North to north and north to
yeah,
south.
and this one here.
so the top ones.
North and north
So,
to south.
we have the top ones.
Yeah.
Yeah.
The top ones.
North south.
Yeah. So now you have the bottom ones.
Mm-hmm.
So, oh look,
But what's
it's the
di-
same.
What's the direction?
Um,
Can't see because of his face, and that one doesn't have a direction.
Can we just
Yeah,
take a
it's
look
up
at it?
there.
Just open it
It's-
up.
okay.
Towards that, and on the left, on the right is towards that. Shouldn't you stop the?
I need to pause the video when he's.
Just copy
is-
it,
Yeah, I'll screen capture it and replace it then. Oh, good. It's only 2 minutes. Oh no!
What?
No. What's wrong?
Sometimes they do this. Oh, okay, no,
No,
it's fine. Yeah. Oh, there we go.
It's moving up.
I want the last one.
There.
Come on.
So it's it's the opposite thing.
Oh, can you put subtitles? Maybe it will give us a.
There it goes.
Hey. Okay. Right.
Yeah, pause.
Ah, no. Hang on. Move. No. Come back here.
There was
One frame.
Yeah.
Yeah.
That way.
Yeah.
That
Yeah.
one, that one.
I,
Well, you can see it. You can see it. So we know that it's going to the right.
yeah,
And that way.
it is moving away.
Yeah. All right. So, there's no arrow here, but what was it? It was to the right, wasn't it?
No, it's
No, to the left now.
To the left?
Yes.
Yeah.
It's
Well, anyways, we know that.
Oh, yeah,
it's
okay.
Coming to the right. So.
Right. Okay. So I think it would be great if you draw these 4 pictures instead of the 2 I have. Lenz's law, yeah. Yeah, I think you should draw these four. My goodness. Did you draw the four?
Mm.
I'm surprised you care so much about Lenz's law. I don't know.
It's weird.
Isn't it good to have?
No, it is good. It's good to care.
So did we ever tell you the name of our lesson?
Rick and Morty.
No.
Bojack.
No. It's quite. It's not that.
South Park.
It's not hard.
It's not like
Nothing at all.
Gives a clue.
who's that?
Is it dirty?
No.
No.
Alright, what's it then?
Maybe engineers.
Maybe.
Alright, continue. So,
Wait. Wait.
oh, which one are you drawing? The last one?
Kind of. Just need that.
Did you get a YouTube strike if you put that?
I don't know. It's only a screen capture.
Okay.
Yeah?
Yeah.
Right, now, so far we know that a moving magnetic field will cause a current to flow. And we know the direction is to oppose the field. But what we don't know is how to calculate the voltage. So Faraday's law lets us calculate how big the voltage will be when we move the magnet. Okay? So what Faraday said was the voltage is equal to minus n times the change in the flux over the time taken. Now please note that the minus is in fact Lenz's law. That the minus is telling us that the voltage is opposite to the change here. Now often in the exam, always in the exam, they don't care about the direction. The question is always, how big is the voltage? Yeah, but you guys really wanted to know Lenz's law, so I didn't want to disappoint you, okay? So,
I was under the impression we were gonna have to know, like, state which direction.
no.
No?
They care about the calculation, really, only. So this is Faraday's law. Okay. Can I continue? You got Faraday's law? Yeah? The n is how many loops you have. Yeah.
Did you change to capital N again?
Did I?
Yeah.
Ah, okay.
How would Weber's over time?
Yeah. Well, remember, what was the unit for Weber?
Oh, yeah, it's-
Volt seconds.
Yeah, volt seconds.
So, yeah. Okay. So, if we move a magnetic field around a conductor or a conductor around a field, then can we use this to generate power? Yes. Behold, the AC generator looks remarkably similar to the DC motor. Here is the AC generator. Now, there are some differences to the DC motor. So, I know the picture's a bit small, but so what's the same? Well, you have a north, yeah. You have a south. These are all the same. But there's a little bit of a difference here with the connections. Can you see what's different between this and the DC motor? What's different?
They're separated.
Yeah, there's two separate rings. With the DC motor, it was like this, not touching. Or I'm rotating, you know. Whereas this, there's two separate rings, okay?
And one cable passes through the other here as well.
Yeah, you can't quite see, but this one here passes through the first one and connects to this outer guy. And this one here connects to the inner guy. And are they connected with a wire, or how are they connected?
By the brush.
By the brush, so they don't tangle, you know. Here's the brushes here. So, you can't see this as well, but I suppose on the inside it would have to be... Oh no, sorry, I'm so sorry. This is attached, and the brush is here.
Yeah.
So,
It's attached on the inside.
yeah.
It's on the
So
outside.
it's kind of like, if I show you here, if this is the outer one, okay, you have a connection here to it. So it, as this turns, it turns with it. But then the wire is connected with a brush. So the wire does like, the wire isn't connected like this. It's connected with a brush. I don't have a brush, but it's only touching it slightly, so it moves like this. Whereas the other end is stuck to it. Okay. So what do we get here? Well, something interesting happens. You get a current through the copper brush here. Now, what's interesting about this current is it actually keeps changing directions. So first the current is heading this way, and then it flips and heads the other way. So the current goes back and forth. And that's why it's called an AC, alternating current. Now, before you draw that, just recall from the formula, you don't need to write this down, but you will need to draw this in a moment, that the voltage is equal to this. Okay? But remember that flux is BA. And let's ignore the minus N for a moment. Just ignore the minus N. How does the BA change? Well, the normal to the plane is rotating, makes an angle theta with the field. So recall from the first lesson that all we do is add in a cos theta. So we get BA cos theta.
So it's a wave.
Yeah,
AC.
the BA is constant. Does the B change? No. Does the A change? No. So really, we just need to know how cos changes. But you know from maths class how cos changes. It's sine. The derivative of cos is sine.
Negative. So.
From maths class. Yeah. And then the other minus I ignored earlier. So in a moment, what we'll see, I'll let you draw this first, is that the voltage graph looks like this. It looks like a sine wave. Voltage increases, then decreases, then increases, then decreases, like this. Yeah. But before we write that, we need to draw this.
Which one is more, how do you say, like it takes less energy. It's more, how do you say, efficient.
What?
Which motor is more efficient?
Oh, well, this isn't a motor, this is a generator. So what you do here is you crank this, you turn this manually,
All there.
and then it generates the current here.
Yeah.
I mean, this works well. This is how they generate power in power plants.
But don't they use like a static wound coil and they move the magnets instead?
I think the more sophisticated ones, yeah. I mean, okay, this is very simplistic.
Yeah.
I guess if you got light enough and strong enough magnets, it might be more efficient to rotate them around the conductor. Yeah, it's probably a bit difficult to get ginormous, 100 kilogram magnets. I don't know exactly, Zach. This would be a very simple generator, you know.
What's the
Not
black
that
thing
efficient
again?
as
Say again?
What's the black thing again? The black square? It's
Just a resistor.
No, where is it?
So this could be your bicycle light, and this could be you cycling.
Mm.
You know.
Mm.
Did you draw this?
Not the-
Continue. Continue, guys. Yep. Diego. So look, they sometimes ask you also to draw this graph, and this shows you the different voltages at the different angles. Okay. So in the exam, it would be typical for them to say, draw the voltage output with the positions. Now, you notice that for half the cycle, the voltage is positive, and for the other half, it's negative. This means the current has changed direction. Switches like this. Interestingly, the voltage increases and decreases and changes direction. Will we look at this? No. Okay, so if you can draw that. Continue. You got that? Okay, so look, we haven't actually said properly what AC is. So what's an alternating current? Zach, you seem to know this word.
It's
Current.
Yeah, it's a current in which the flow of electric charge reverses direction. Whereas a DC current, what's that?
moving in one direction.
Yeah, the flow is only in one direction. Okay, so I think it'd be good if you can write this down. Okay, you got that? You guys are mad on drinking giant bottles of water. This is...
Yeah, he just went over to close.
Alright. Next definition? Yeah? So look. The voltage of an AC can vary from minus Vmax to Vmax. This makes calculations a little bit difficult to do, right? Because we said in physics we like our values to be a constant when possible. So how do we normally fix this in physics?
This, oh, sorry, no, that's maths.
Yeah.
Absolute value.
Yeah, but we still have then, absolute value is good, but then we still have the problem of it going from 0 to Vmax.
Just say the magnitude.
Yeah, but what value should we use?
Could you convert it to DC?
The positive.
Well, I mean, what number? You know, if I said to you, like, take for example this voltage here.
Plus, minus.
Yeah, well, let's say this voltage here is going from, let's say, minus 256 to 256. And I want to use a formula like V equals IT or whatever. Well, what value of V do I use? Do I use 256? No, because that's too big. Because it's only 256 briefly.
You use an average.
Yeah, but what's the average of minus 256 and plus 256?
Zero.
0. But then you suggested we use the absolute because we don't care about the direction.
So it's one card.
So maybe it's between 0 and 256. Anyways, the other problem is that the graph is not linear. It's actually curving.
Mm-hmm.
So we won't do this on the IFY, but there is a way to get the average of this graph. The average voltage is, anyone want to, it's not Vmax over 2, it's Vmax over root 2. Now that's only true for this graph because it's a wave. Your average is not half but 1 over root 2 of the maximum value. Now would this make the average bigger or smaller if this was a 2? If it was a 2 it'd be smaller. So the root 2 here is making the average bigger, isn't it? No, sorry. Root 2 is 1.4.
So it's bigger than normal.
It's making it smaller than, yeah, it's making it smaller. And the reason for that is if we go back to this graph, being at the peak is kind of less common than being kind of at the bulkier parts nearer to the axis. Anyways, it doesn't matter. It doesn't matter. This is the formula for calculating the average for this type of graph, okay? Sometimes in the exam what they'll do is they'll give you this and they'll want the average voltage. Now, note, this here is 220. Is that 220 the average or the maximum? Does anyone know?
Max.
No, it's the average.
Oh.
So actually this hits higher than 220 on the peaks.
So it's around 4 something.
Well, you could calculate it. It would be 220 times root 2.
311.
So this is actually plus or minus 311 on the peaks and the crests. The crests and the troughs, I mean. Okay, do you have that formula?
Why is AC and used over DC?
AC is used because the generator on the previous slide produces AC.
So just because all the generators in the world are AC, we use
It's
AC.
expensive to convert it to DC.
And which one is better?
DC.
DC.
It's more useful, yeah.
Well, it's transport's better.
So high voltage lines
More
are DC.
powerful.
No, they're
Yes.
AC.
They are AC.
But they should be AC. They should be DC. But it's too expensive to convert them to DC for transmission. So they get transmitted as AC, even though it's less efficient. It's just cheaper.
Okay.
Those AC power lines are inefficient. It'd be much more efficient if they were DC power lines. But DC is expensive to produce. So
Actually,
it's a, you know,
converters and stuff.
like what do? You want to save money, so you don't convert it, but then you don't want to waste energy. You know, it's which is more important, saving money or saving the planet? Well, what do you think private power companies would choose?
Saving money.
Saving money, yeah.
Is it expensive in so to convert it because the how you call it, the transformer costs a lot, or because each day you lose money by converting it?
No, I think it's just the equipment is
Cost.
very expensive.
Okay, so in the long run it will be beneficial.
Yeah, maybe, but the equipment has to be maintained as well. It's very expensive. It's very, very expensive. Now, that might change in the future. Because when you think about it, all your phones,
They are DC.
they convert the AC to DC. You know? Okay, continue.
Yeah, not even light bulbs use AC power anymore.
Not the energy efficient ones, definitely DC. Yeah, that's true actually, yeah. Is there any handy way to figure out which way the current will flow? Yes, there's quite a handy way. This is Fleming's right-hand rule.
Oh,
Yeah, so let me explain here, okay?
It is the one that we were with.
Hang on.
It's the same but opposite.
Yeah, I'll give you an example. Guys, can you look up? I'll give you an example, okay? So, let's say this is the armature, and I'm here, and I'm rotating it to generate the electricity, okay? And let's say there's a magnetic field, we'll have it go into the window, okay? So, the magnetic field is from north to south, it's pointing this way, okay? And I want to know, for this part of the armature, which way will the current flow? Will it flow towards you, or will it flow towards me? Okay.
Which way?
So if I use my right hand rule, okay, the motion, if I'm rotating it this way, the motion is up here. So this is up. The field, which way is the field? We said to the window. So which way is the current?
Towards us.
Towards you. Yeah. So if I'm rotating it this way, then the wire that comes out here, the current will come out this side.
And that will only be until it's at 90.
Yeah.
And it will be
And then
decreasing.
When
until
it's
it gets
over
to-
here,
Yeah. It's
uh,
completely flipped.
it's flipped around then. Let's try it on this side. Force, which way is the motion?
down.
Down now. The field, that way. So the current now,
So
this direction instead. Yeah?
So wouldn't the two currents be opposing each other in the conductor? Because it's not like.
That's why the two rings are separated.
Oh.
Yeah, I think you get big problems if you. Yeah, no, this is separate. Yeah. Okay, so we have Fleming's right hand. No, was it Fleming's right hand grip rule or just right?
Fleming's right hand motor rule.
no, it's a thumb rule.
Right hand
That's
grip.
Faraday.
It was right hand grip rule.
Yeah.
Fleming's left hand rule for calculating the force, and now we have Fleming's right hand rule for calculating the current.
Inductive rule.
Yeah. Whew. Okay. Copy this in your notes somehow.
You got this. This one is alright.
You didn't see my one looked like.
Retarded.
Looked like Ezekiel from Scary Movie.
Continue? Yeah? Continue, guys? Okay, so, note, normally, the delta flux, it's either the B or the A that changes, but for our problems, not both, which is good. So either you're changing the B, or you're changing the A. but you're never changing both at the same time, which is good. So our delta flux either is A delta B if you're changing the B, or it's B delta A if you're changing the A. The delta B is if the B changes, and the delta A is if the A changes, obviously. Usually a swept out area, which I need to explain in a moment. I'll draw this, and we can rewrite the formula. Yeah. Okay, so before I do some examples, I have to... So long you.
You don't want the screen cap on.
Ah, it's okay. I'll try and find some nice something.
But like sorry, we're having technical.
Right, so look. I'll give you two examples before we look at the examples here. So if you look here, there's my conductor. Okay, and let's say you have a magnet here, north-south, like that. Okay, and just to be clear, I don't. Oh, thank you. Well, anyways, just to be clear, I don't care about the direction of the voltage. I only want to calculate the voltage. Okay. So let's say this is, let's say it's 2 Tesla, for example. If I think about, and let's say this is, let's make it easy, let's say it's 100 loops. Okay? What else do we need to know? Oh yeah, I need to know the area here. So we'll say it's a circle, and we'll say radius, we'll keep it 3 centimeters. Okay? It's okay. It's not too bad.
Is it the thickness of the wire or the thickness?
No, the thickness of the entry for the bar magnet.
Will it affect the thickness of the wire?
I don't think that's too important.
But it affects one.
Oh, it will, yeah. Now, let's do the calculation for the voltage. And remember, I don't care about the sign, okay? So that will be N delta flux over delta T. What's the N? 100. Now, we have to do a time calculation. So this is what I'll do. I'll say, first the magnet is here, and then 0.25 seconds later, it's inside the coil. Okay? So I know what the delta time is here. What is that?
It's
0.25.
25.
Okay. Now, what's changing here, the B or the A?
B.
The B is changing. Is the area changing?
No.
No. So it's going to be A delta B. Yeah? So let's simplify this a little bit. This would be 100. A is pi or squared over 0.25. And now we really need to think about the delta B. The delta B will be B2 minus B1. Anybody have any ideas what the B2 and the B1 are?
Or which point do you take the magnetic field from? The start of the coil.
What do you think? Yeah.
So
Will you tell me what you think B2 and B1 are?
B1 is 2 and B2 is 2 and B1 is 0.
Yes, that's it.
It's true.
So at the very end in the story, the magnetic field is fully inside the conductor. So you have 2 Tesla. At the very beginning, okay, imagine that this is far away. There's no magnetic field. So what has the change here been? We went from 0 Webers to 2 Webers. Right? Yeah. So this is the voltage here. So Diego, do you have that typed in?
Yeah, so it's 2.26195.
2.261,
26195.
yeah, volts. Yeah. Is that, do we get the kind of idea behind this Faraday's law? Now, I know there should be a minus, but like I said, I don't care about the direction. So if you want to be particular, there you go.
faster you move the magnet.
Yeah, if you were to move the magnet quicker, what would happen? That this number here would be smaller, which would make this here bigger. Yeah, so if you fire the magnet in faster, you get a higher voltage. Also, if you had a stronger magnet, increase it as well. And what would be the effect of changing the area? Well, if you increase the area, would you get more or less voltage?
I would say it's increasing
You
up
have
to
to
a
increase.
point.
Up to a point, exactly.
Both.
If you,
It would
yeah,
be linear up till a certain
if you
point.
increase the area, you would get more voltage. However, you have to make sure that the magnetic field still extends out to that area.
You get
So, and magnetic fields actually close quite rapidly. They have a very limited range, you know. Yeah, Diego, what did you change?
So I changed the area from 0.03 to 0.3, and it increases by 100
Yeah,
to 26.
yeah, but you would need a massive magnet to make sure you can get that area. Is that example okay, guys? Yes or no? Are we okay with that? I'll give you one to try now, and then I have another example to do.
So do we do them with direction as well?
In the exam, they never care about the direction. I'll give you another example. Well, can I scroll down to it? Well, when you're ready, I'll just put it at the bottom here, okay? Okay.
Will it change if we only increase the size of the magnet? Not really.
The dimensions of it, like the length,
The area.
Right.
No.
it's just yeah. Okay, so we'll keep it similar. We'll say the radius now is 2 centimeters. Okay. I'll put the magnet in. The magnet is already inside to begin with, and we'll say that the magnet is 3 Tesla. Okay, and north and south is there if you'd like to know. Oh, and we'll keep it 100 turns. And then what I do is I flip the north-south over 0.5 seconds. So what I do is I take the magnet and I go flip it around inside. Yeah. So it's a small. The length here, obviously the length of this magnet has to be less than 4 centimeters, so you can flip it around. Okay, so yeah, not that it's important, but you can make it 3 centimeters. It's a little bar magnet. You flip it around. Okay. Right. Give me the voltage that is induced. You got that? You got it? What you got?
0.
0? No.
Well, that's what I'm thinking. If
0?
you
No.
change it to.
No. Let me show you.
But
So this you can write as NA changing B over change in time, right? Okay, what's the N?
yeah, it's 100.
100. The rate, the area is 0.02 squared with the pi. Fine. The time?
0.5.
0.5. Now, the difference here is in this situation, if you call this one 3 Tesla, when you flip it around, then it's minus 3 Tesla,
So this is
the opposite direction. So it'd be 3 minus, minus 3, minus 3. But I don't care about the minus anyways. So 6 Webers is the change. Now think about it. If you go from plus 3 to minus 3, or minus 3 to plus 3, that is a difference of 6. Yeah?
That's what
What's wrong, Zach? You're making that face that you don't like something you see. What's wrong?
No, no, it's
it's 1.507. Zeros, yeah.
Yeah?
That change from minus
Is okay? Yeah? Yeah? So you could have the magnet spinning inside and you'd be generating a current. Actually, yeah, if you could think about this, if you could keep this spinning with a periodic time of half a second, so what's that, 2 hertz? Have this magnet rotating at 2 hertz, you'd get 1.5 volts. That should be enough to power your calculator, right? Yeah.
from
Yeah.
which direction the current flows is in the street.
Yeah, but if you can connect an old light bulb to it, it won't matter.
Yeah.
Anyways, it's actually quite simple to rectify the current, so you force it to travel only one direction. You can use a diode to do that. Okay.
What is the unit for number of turns?
Yeah, they just call it N, but I don't like that because that's not a real unit. So they would say in the exam like N Webers, but it's not.
It's all linked to that Weber
Yeah.
definition, right?
No, not so much. Right, the next one now is what do you do if you change the area? I'll give you an example here. Let's say you have north here, and I'll try and draw this 3D, south here, and this is going into the page. Okay? And then what you have here is you have a copper wire running this direction. Do you know what? I think I'll do it the proper way. So here's my magnetic field. It's going into the page. Okay, so B is into. And then I'll put my conductor going this way. And what I'll do is I'll say it has a length L. Okay, and I'll drop it at a speed of V, constant. Or I'll move it at a speed V. So just to give you a picture in your mind, imagine the magnetic field is going towards the window. I take a conductor here and I move it up and down like this, inside this magnetic field. What will happen to this conductor? I'll get a current, won't I?
Alternating.
Yeah, do you understand? It's the same picture at the beginning of the lesson. At the beginning of the lesson, the conductor was fixed and you moved the magnetic field. But do you understand that that's the same as the magnetic field is fixed and then you move the conductor? There's no difference, right? So in this picture, the magnetic field is constant, but now you move the conductor. Yeah? So we want to calculate what's the voltage we get here. So let's calculate it. Now, you can use Faraday's law, but Faraday's law can be simplified here. Now, in this picture, there's only, normally in the exam for these problems, the N is only 1. It's like my pen, just one conductor. Okay, but you know, you could have something like where the conductors may be looped around and you move it up and down. Okay, but normally it's just the one. Right. So according to Faraday, the EMF will equal delta flux over delta T, and in this case it's 1, and we don't care about the sign. Now, what is changing here? Is the magnetic field changing? No, that's fixed. So it must be the area that's changing. But what area is changing here? Now, it might help if you look at my pen and visualize it. What is the area here that's changing? Which area? Like this area. The area I'm drawing with my hand. That's the area. So, for example, at the beginning, there's no area. Then as I drop this, I draw an area. So, what is the area here? Well, let's think about the distance, speed, time triangle. I want to know this distance here. I'll just call it h. So, distance, speed, time. Okay. The delta t. Oh, and the area will be L times h. And the delta t will be h over v. So this simplifies to what? B L V. That's the voltage. So which way did we say the?
It goes towards the.
Which way is the North Pole?
Oh, North Pole is that way.
But hang on, this is east, is it?
No, east is
No.
that way.
Hang on, that's the city centre. That's north, isn't it?
Yeah.
Yeah, that's
North
north.
is that way.
Okay, let's say north is this way, east, west, south. So for the Earth, the magnetic field is this direction. Yeah, like I was pointing earlier. Right, so the magnetic field's going this way. I want you to calculate for me, have I got a piece of metal?
V and V are all constants.
Yeah, they're all constants, yeah. Where's my meter stick from? Okay. So can you write this down? The L is 50 centimeters. So L is 50. I think if you look it up on Google, the Earth's magnetic field from the Earth, the B is something like 20 millitesla. Do you want to Google it there for us, Lynn? It's tiny. Millitesla.
0.2 Tesla.
0.02.
Yes.
Yeah. Anyways, we'll just say it's that. I'm pretty sure it's 20 millitesla. Okay. And now we need a V. So, do you think I could do this at 1 meter per second? I think I could. So, that's 1 meter. Okay. Well, I haven't got my voltmeter, I think, won't detect it. It's too small. But believe it or not, as I do this, I actually get a current here. Because there's magnetic field going to the north.
To the south for me.
Well, yeah, it's pointing to Santa Claus. Magnetic field going to Santa Claus. The length is 0.5 meter, and I'm dropping it at 1 meter per second. So I do get a current here. Now, can you calculate for me how much of a current, or how much of a voltage I get?
So you say 1 second.
Yeah, the V is 1 meter per second.
V is 20 times 10 to the power negative 3, 20 million.
Yeah, 20 millitesla.
It's just half.
So 0.01.
0.01 volts.
Yeah, it should
So
be
small.
20.
Enough to put on there.
Could I measure that?
0.01 volts. So when you do this, that's like 0.01.
Yeah, there's this 0.01 volt here. Could I measure that? That's a little too small, isn't it? 0. I would need a longer. If this was 1 meter, then that would be 0.02. Still too small. Or I could drop it faster. I could. Yeah. I might just about detect it on the voltmeter. Yeah. Obviously, we can't really generate power this way. The Earth's magnetic field is not strong enough. So, this is really, can you see that this is really the same formula as this, but it's more convenient for these types of problems. Yeah? I believe that this is in the formula book as well.
It's the belief formula.
The believe.
BLD.
Did you mention this one earlier?
Believe in you.
Now, I don't think I need to do these examples because I've already just done them. Yeah, I've done them. So, there is 5 minutes left. Can you have a start on your homework then?
I just have a quick question.
Yeah.
How do maglevs move?
How do what?
Maglevs, the trains. How do they?
I think it's a solenoid.
But if they are flotating between.
Flotating.
Well, I mean, you know, like when they are like in a magnetic field, how do you create a force to move it? You use it like
It's the current. It's flowing through the
Yeah, maybe the magnets are just at an angle.
It's
Sure.
repulsion.
yeah,
Well,
no, I know, but like
But he
repulsion, so
wants
you
to
have
know the
squeeze
forward motion.
it. Yeah, the forward. I get that they, you know, like just south to south and north to north, and it just repel, so it will flow. But
I don't know. I need to look into it. There must be some reason that these never really took off. Maybe they're too expensive. So I've never seen one in real life.
I have
Yeah, where?
in Tokyo Airport, I think they have one.
I
But
know.
it's
That's
like
That's
small.
different. That's Tokyo. That doesn't. that doesn't count. That's futuristic. I've been anywhere in Europe.
Oh, there is one in Germany, I think.
Is there?
Yeah.
Really?
But also for like small areas.
Yeah.
So
There has to be some reason it's not mass produced.
Are high-speed trains all language?
Are they?
No. They are normal railroad thing.
The bullet train
Bullet train is also
is normal.
standard, yeah.
It's not mag. Yeah, I would have thought you needed something fancy for the
No,
bullet
just
train.
The 300 case an hour you can.
Okay, fair enough. Right, get started on these. How many did I give you there?
6.
So you would like
6?
switch
That's all right.
Yes, yeah.